Okay, so I wanted to say hi. I'm Jason. This is Trolls. I'm one of the multi-platform leads in Google Workspace, and Trolls leads the Kotlin compiler team in Android. And I'm here to talk to you today about Google Workspace's journey through Kotlin Multiplatform and what we've been doing with our experiment and where we're at today. And Trolls is here to fill in some of the technical details of our work and to correct me whenever I lie to you.
That's a lot of responsibility.
Okay, so multi-platform in Google Workspace. Google Workspace has actually been doing multi-platform for more than a decade with internal transpilation tools. We've been taking Java and transpiling it into Objective-C and into JavaScript. And the reason we've been doing this is for consistency across platforms. We want feature consistency, bug consistency, more importantly, bug fix consistency. And that is the real key reason, is we want the same user experience for all of our users across the platforms. Now, with that, you do get developer velocity, but you need to do an upfront investment. Anyone who tells you that multi-platform is free developer velocity, it's not actually true. You do need to have discipline and make an upfront investment there. It's not just quick 3 times developer velocity. There is a cost upfront to learning and building that rigor. So multi-platform is used by all of the Workspace apps. And that's Gmail, Chat, Calendar, Docs, Slides, Sheets, all of the productivity Google apps, and by different extents and different ways in each app. And we target business logic. And what I mean by business logic is basically anything that's not the UI. So synchronization, page layout, scheduling, anything you want to be consistent across platforms, and that an inconsistency would be a bad user experience, because that's really important. And I talked about the transpilers, really quick plug. The Java compilers we use, one was called J to Objective-C, Java to Objective-C, and J to CL, Jackal, Java to Closure. Those were our transpilers. This whole system, they deeply embed Java into the target language, whether that's Objective-C or Closure. This is well aligned with the way Kotlin Multiplatform allows us to work with business logic, and this is why we decided to start on the experiment. Can we move into the wider Kotlin Multiplatform ecosystem? And so what we did is we already had 2 transpilers, and we had this giant code base in Java. Why not write a 3rd transpiler? So we wrote a transpiler to take Java and turn it into Kotlin. And what we have is now our giant code base in Java, we now transpile to Kotlin, so our developers are still writing Java code right now, unfortunately, but we're able to generate Kotlin code and ship code that's running, built by the Kotlin compiler, and run a experiment where we can directly compare code built with our Java multi-platform system versus the Kotlin multi-platform system, and compare it and provide feedback and help improve the Kotlin multi-platform ecosystem, and make the decision if we want to commit long-term to Kotlin multi-platform, and do this in a rigorous, well-thought-out way. So we've been working on this experiment, and we have results for the experiment. And so at a really high level, I'm going to just hit with the headlines. After the experiment, we consider Kotlin Multiplatform validated in our Google Docs experiment. And what I mean by this is we consider the experiment a success, and we're going to go ahead and move Kotlin Multiplatform to the entire Google Workspace ecosystem. So we're going to proceed with this transition. We're actually very happy with it. Currently, right now, KMP is active in some large percentage of Docs users. And the exact percentage varies depending on what experiment we're currently doing and actively working on as we are still tweaking things and working out details. And I said we have a rigorous A/B experiment. What I mean by that is there is a experiment population that gets randomly selected of the docs users, and there is a control population that is, again, randomly selected in the same way, so that we can rigorously compare latencies, memory usages, crash stability, and actually get production data that we can tell from users, does Kotlin multi-platform affect this? Can we make sure we deliver a really good user experience to our users? Because that's what we really care about, right, is does this work for our users? We know about the Kotlin experience for developers. We just want to validate it for our users. So what we studied precisely, I talked about this. So we ran the experiment. We've been running the experiment for about a year. And we validated runtime performance, memory usage, stability, crash rate information. We also looked at the IPA size and build performance. I talked about IPA size because the area with the most significant change is Kotlin native. So when I focus on numbers today, I'm going to be mostly focusing on Kotlin native. The last two, you don't need a production experiment, but we monitored them over the year. So the results are interesting. Okay, so what I mean by this. So J to Objective-C, Java to Objective-C, we know from our studies over the last 15 or so years that it produces Objective-C code that runs approximately performant to equivalent Objective-C, handwritten Objective-C code, with the caveat that Java developers don't write code in the same style as Objective-C developers. So we know that our J to Objective-C code is comparable to Objective-C. So we can say that we're comparing Kotlin native to approximately similar Objective-C code. So, but the environment in the world is really, really different, right? So Objective-C has different calling conventions. It has a different runtime environment, right? It's reference counted, where Kotlin native has this active garbage collection system, several to choose from, in fact. You have calling conventions, garbage corrected. You have a whole runtime optimization system that Kotlin native has. You pay for that in build performance, but Objective-C doesn't generally have a whole program optimization. So there are all of these factors that come in to make the whole ecosystem very different, and you see these artifacts in results there isn't a simple way to talk about all of the results. That said, I'm going to make some broad, sweeping generalizations initially, and then dive down. So performance generally has been on par or better than our Objective-C code in docs. In the major metrics we measure, which is a really fantastic number for Kotlin native. There is a split where things become interesting along what I'm calling short, tight loop metrics and application-wide metrics, and I will dive into what that means in a second. So the memory profile of your application changes dramatically. And when you care about critical performance, you have to think about what the GC is doing. And this is just your life in the Kotlin native world. For us, we test often because things change. So, for example, some of the tricks or hacks we have done to improve performance, we've removed as Kotlin native has improved over the past year because they were either not necessary or counterproductive, as the JetBrains or Trolls team took our feedback and improved the ecosystem. So, tight loop metrics. So I'm talking about metrics that are in the 10 to 50 millisecond range. We saw an improvement of 15 to 20% across the board in all of the metrics we measured in this range. That's And that was out of the box at the beginning of the year with the experiment. No work necessary. Kotlin native had that speed improvement. So, a little bit of analysis, thoughts on the implication. These tight loop metrics tend to be the metrics you're measuring for short user interactions. These are the things that make your application feel snappier. That's the type of thing you're generally describing when you're measuring these short time frame interactions. The other thing you can kind of deduce from this is that straight line code or small sections of code or tight loop code is executing quicker for some reason. And you can think about like the optimizer running or other interpretations on why this might be happening. But from like production metrics, we know that this is true. Okay, application metrics, the 500 millisecond, were metrics that you were scaling at 500 milliseconds plus. So these, on average, had no difference in performance for J to Objective-C. So they were like right on average the same amount of runtime, or approximately the same amount of runtime with the kind of noise you would expect from large data sets. When you reach the really, really high percentiles, so that's the average, right? If you talk about like the P90, the P95, the P99s, you'll see a little bit of improvement, like 2% or 5% improvement, which for long-running metrics at P95, P99, that's actually a lot of milliseconds. But generally at the average, again, they're about the same running time. Okay, interpretations, analysis. What we believe you're seeing here is these longer running metrics. You, on average, statistically, are catching a garbage collection pass inside these metrics. And we believe that's accurate because one of the things that we saw really strongly affected these metrics was tuning the GC. And if we made a mistake tuning the GC, we would see these metrics get significantly worse. So we believe that that kind of catches all of that. And so why do you get that tail end improvement? Well, the guess, if we're guessing, is that the kind of straight line performance improvements eventually begin to dominate as the runtime gets longer. Okay, memory usage. It's a trade-off. You use more memory, you get more speed, because you, again, are paying for that GC. You give the GC more room to work, it can do things quicker. So where we ended up as we played with some of the dials that Kotlin native gives you for the GC and how much memory it will use, is we ended up deciding we're going to spend a little bit more of our memory budget to get more performance, because we decided there's more RAM and users like performance. But you do have that trade-off, and you can make some of those decisions. So now I've talked to you about some of the statistics, some of the numbers. I can talk to you about how we got there and what we did. I've talked about the garbage collector a lot. I can talk to you about some of the things we did with the garbage collector. Early in our study, we just started manually triggering the garbage collector. We found a data structure that we interacted relatively regularly with, and every 10,000 interactions, we would trigger the garbage collector. This is actually a trick early JVMs did. They had, I believe it was array list. Every 10,000 accesses on an array list, they would trigger the garbage collector because the JVM had bad heuristics. This is what we did earlier on. Then we moved from parallel mark and sweep to concurrent mark and sweep. Highly recommend. It made a really big difference for us. We removed that manual triggering when we made the transition, and that brought a huge amount of performance back, but we were using more memory again. So we then were able to tune down concurrent mark and sweep a bunch without losing any performance. And the tuning characteristics for us, and this will vary by your application, what you're doing, your processing, what your big tasks are, how big your data structures are. We changed its heap utilization threshold. So how much of your memory are you using before it decides I need to do my cleanup work at 75%, and then we gave it its initial heap allocation, how much memory you're going to start off with. We bumped it up from the 10 megs it starts at to 25 megabytes. And again, this varies on the size of your initial data structures. Do some testing, and this can have like a dramatic impact on your kind of initial performance metrics. Oh, last one. If you have a screen where you're waiting on a user to make a decision, and then you're about to do a bunch of work, triggers the GC. That way, the GC is not going to run when you do your bunch of work, because the device is doing nothing while you're waiting for the user. Might as well use that processor time for something. And that's what I just said. Strings, the bane of my existence. There were two major problems with strings. They caused performance issues crossing the boundary between native code and Kotlin native. They also used up. They also had a lot of size problems, both in memory and on the IPA. And this is the UTF-16, which has the nice effect that they match identically to the performance characteristics guaranteed by Java in the language spec, and so you get the same characteristics. However, they are not the same way iOS encodes strings, and so you have to re-encode your strings, and you lose some of the performance gains. I'm going to nerd out for a second, because I find this cool. You just throw something at me if you're bored. Objective-C strings are kind of interesting. So they're a class cluster of actually a bunch of different classes. So they can encode them as ASCII or Latin 1 strings. You get the aforementioned UTF-16 strings, or they can be a tagged pointer. And so a tagged pointer is a way for the VM to encode your entire class in a single pointer. So you get a bit, a class key, and then the rest of the pointer is actually the entire data of the class. If you've ever wondered in Java why integers between negative 128 and positive 128 are always guaranteed to give you the exact same object, it's because they're tagged pointers. It's a trick you use to optimize memory. iOS does this for strings if the length and the combination of the string fits in the pointer. And they do that with 8 bits, but you can also encode the characters as 7 bits, 5 bits, and 4 bits. And how do you do it with 4 bits? Well, you encode it in a Huffman table that doesn't include all the characters. It's actually fascinating, insane, and I have no idea how good it is. And I'm not going to take credit for this. This is actually a fascinating deep dive article by Mike Ash. It's an old article, but it is absolutely fascinating and fun to read. I absolutely recommend it. This is your turn.
Yeah, so Jason asked me if I could do a slight deep dive into what we've actually done for changing the representation. So before this change, strings in Kotlin native were just identical to being a primitive array of UTF-16 code words, and it's really convenient for being consistent with the JVM, because there everything is UTF-16 based. So just having it be an array of UTF-16 values, it's not a class that wraps an array like it is in Java. It is a UTF-16 array. And we still kind of need to use that to have it work with some of the legacy code. So it still needs to be a UTF-16 array, but what we store inside that array can change a lot. So the problem here is that for a lot of strings that you encounter, UTF-16 has a lot of wasted space. If you're just using Latin 1 characters, which is very common in source code, for instance, and a lot of the source code ends up in the binary at the end, every other byte is basically going to be 0. You only have very small numerical values in there. So if you look at the string hello, it'll have a 0 at every other byte. This is, of course, not a new problem. This has been solved before. It was solved way back in Java 9 on the Java platform, where there's a small bit in the header saying, is this backed by an array of chars, or is it backed by an array of bytes? And we're kind of mimicking this here in this change, where we're saying, well, the first 16 bits of the string data actually encodes a little bit of information about it. It encodes whether it's UTF-16 or Latin 1. Additional representations could be added later. And then whether the hash code has already been computed. So this change also caches the hash code of the string. And that means that if you enable this is still under a flag, so you need to enable it to use it. You can have a string representation where whenever possible, whenever the strings only use the first byte of the UTF-16 value, it can be compressed down to using only 1 byte per character, plus this 2-byte header on top of it.
So we use this by default in our build system, and it has made a huge performance impact as well as an impact on binary size and our space and RAM. So stability. So we carefully monitor the crash rate of all of our apps, and so we monitored this in the controlled experiment as well. So the exciting thing is there's nothing to tell you here. There's no significant difference at large scale between the crash rate of the Kotlin native runtime or Kotlin native compiled code between our control and our experiment. I know, boring slide. We did find a very low rate race condition in the garbage collector through the experiment, which I guess tells you the signaling for the system does work. We can find things, and the takeaway I kind of want to take here is we're watching, and so we're finding small-scale problems so that JetBrains can fix them, and they get the signal there so that Kotlin native is rock solid. The bug number is here, and it is absolutely interesting.
Well, then maybe you should, so I can actually see what's going on.
One more time. Come on.
No? Woohoo! Yeah, so this is just a description of what that bug was, and it's an exceedingly rare thing to occur. So this bug had been in Kotlin native for 2 years at this point, and it was something that on our runs it only showed up in 1 in every 100,000 app starts. And it was only possible to find this really rare race due to crash reporting, and it's really just a fairly easy initialization error that has been around for a long time. There's some global data. As part of that global data, you initialize a thread that does GC scheduling on a timer-based, and sometimes that gets triggered before the global data is fully initialized, and then that ends up accessing uninitialized memory, and then the app crashes because you can't do that. So once you see what the error is, it's of course you might say, well, why didn't you catch this? This is concurrency 101. As I said, the bug had been around for 2 years and many deployed apps, but
So again, like the takeaway is like our watching for crashing and stability is super, super sensitive, and so the Kotlin native runtime is actually very stable and production ready because we can detect things that are like 1 in 100,000 app startups, and JetBrains is willing to spend the time debugging and fixing them. So IPA size. So IPA size ended up being comparable to J2 Objective-C in the end for most slices. The string change was critical to this. It was not until we actually changed the strings from UTF-6 from the UTF-16 to the other encoding, because that change doesn't just affect in RAM, it affects like the encoding of constants in the IPA. There is also an addition of a tree shaker to the Kotlin native compiler as an extra flag that we do to add more precise entry point information to the Kotlin framework generation. This explicitly gives Kotlin native the entry points we use by Objective-C and Swift. And this makes the app a smaller IPA, smaller in memory, runs faster, and optimized builds run faster. Why aren't you using this? Because you can shoot yourself in the foot with it a lot. We're taking advantage of a structural design in Google Docs that allows us to know precisely what the entry points are. We are building out a tool to automatically generate most of this list with like the caveat that Objective-C, you can generate selectors dynamically at runtime, and if you do that, you need to specify those manually, much like writing R8 configuration files, you have to manually specify things you do in reflection. Build speed, everyone's favorite topic. So I'm going to put a caveat in here. Everything I'm talking about with build speed is our build system based on Bazel, where we're starting up compiler actions as a cold start. So this is not necessarily representative of what you're doing in Gradle. So each invocation of each package is a new invocation. So also, I want to emphasize you are getting what you're paying for with the compiler. Like I said, you're doing a whole program optimization step that you don't get in Objective-C or Swift classically. The Kotlin language itself is more expressive, and that does take more work. That said, we did some work to add what we call klib headers, which give us some compilation avoidance. Basically, we only rebuild, it lets us do some structural rebuilding. And we also moved a bunch of the work out to the leaves. So we moved a bunch of the binary generation from that framework build step to the klib level. Right now, these are in our internal Bazel leaves. Lastly, I mentioned that last year we had built out a heap dump tool. It's in the Kotlin native repository now, like the JetBrains repository. And it's super useful for memory debugging. And it was fun to build because we didn't actually have to do a lot of work, because a heap dumping tool, the first step is to walk the heap, and Kotlin native already has a garbage collector to do that, so we just borrowed that and dumped the heap as we walked the structure. And then the other half is displaying that, and Kotlin native looks a lot like Java, so all we had to do was convert that dumped structure into an hprof file, and then we just borrowed someone else's visualization tool. So, like I said, we generate a file we lovingly call a kdump, locally from a system call inside your iOS application, and it lists as structs literally every field and every object in the Kotlin heap. We reprocess them with a command line tool into an hprof file. The reprocessing does a few things. For example, it changes Kotlin string and makes them pretend it's Java lang string, so that the hprof viewer does all its fancy features for visualizing strings and stuff. And then you view it with your favorite profiling tool, like IntelliJ Ultimate. Yeah, I did my plug. So the tool is as easy as calling debugging dump memory from like Kotlin native runtime. It's really low level. You're literally passing along, which is a file descriptor. I've got some random Objective-C code of building the file descriptor to a temporary file. It's on this slide for reference. You don't necessarily need to read it now, but you generate that file. Again, more code that you do not need to read. You build the tool. Right now, it's kind of a lot of work. You have to pull down the Kotlin native repo and build the tool. There's no kind of nice, happy, pre-built, integrated system. But there's a sequence of commands that you eventually get an hprof file. And then you happily get it in the debugger. So what you're looking at is a toy app that I built that these are all Kotlin native objects that are pretending around to be Java objects, and you can walk around and display them. There's IntelliJ, you can use others. GC roots is kind of nice because it will list all of the objects that are held by native as roots, which is a nice thing to kind of find because then you can walk your object graph from like your native code through ObjectiveC. We found that really interesting and useful a lot of times for debugging. All right. Questions, comments, concerns, cries of anguish?